Hey, welcome to our lesson on linear correlation. So this is quotes from Hans Rosling, and so he's just saying, as our world continues to generate unimaginable amounts of data lead to more correlations can lead to more discoveries. One of the greatest decision-making tools in stats is a line of best fit. So we're going to work with the line of best fit today and see how the line of best fit's created. Just a little warm up. You can watch both of these videos. If you're watching this one, we just wanted to see a couple quotes from it um, around the middle, and so I'll put the time, and so really that he does say like correlation is not causation. Um, Correlation is the extent to which two variables are related to each other. That's the definition. So if you want to get that definition down in your notes. Um, and then one of the dangers of finding variables that are highly correlated is that we assume that one variable causes the other variable. This is referred to as causation. You'll focus more on this discussion, but it is important to be aware high correlation does not necessarily imply causation. So this discussion will continue actually in the next lesson, but it's something to think about right away um, when, when we first start the correlation conversation. And so you can watch this video here, and he talks about how it can imply causation as well. So it's not, because we always just say that it can't forever, but it can. So he's got some good points in there. Maybe focusing on doing the scatter plot. And so we're going to look at this Fathom. If this isn't something that you have or you have access to, we just want to see how to actually do the line of best fit. So if you don't, this is something we did in class, but instead of doing it, if you didn't do it in class, then what we can do is you can go here and just see how we can actually like move the line. And so what we're doing is minimizing the square distances from the line. Um, an example that we had before, and so is just with this data Aboriginal identity and non-Aboriginal identity. And so it's weekly wages from 2007 to 2016. We're going to be looking at this data here. Um, so this is the line of best fit. So to recreate this line, you can kind of follow the instructions on the tutorial video through the spreadsheet, but we're just highlighting the data, clicking Insert Chart, and then under Customize for a scatter plot, you can actually go to Series and insert Trendline. You also have to like make sure you're showing the equation, but you're also clicking off showing R squared. In this graph, there's not really an independent and dependent variable. We're just looking at the relationship between the two variables. So this is the equation line, so it should be something familiar to you. Y equals mx plus b. Y is the dependent variable. It responds to the independent variable, the predictor. M is the slope, so the 0.992 in this case would be the slope. For every unit increase in the independent variable, the dependent variable increases or decreases. And this says change, but it is always increase. So we always look at increasing the x, and then what does the y do? And the y-intercept is the 119.586. It really just tells you when x is 0, what is the y value. So with the slope of 0.992, we can say as weekly Aboriginal income increases by $1, the weekly non-Aboriginal increases by 0.992, which is very close to being the same amount. With y-intercept of 119.586, we can say if weekly Aboriginal income is 0, it's kind of a funny scenario, like it would never happen, then it's telling you what the non-Aboriginal income would be. But since we are close to 1, we can see that all along, no matter what the x value is, you're roughly $120 bigger because this 0.992 is so close to 1. That's only true because the slope is close to 1, though. It's not true in any other case. The correlation coefficient, the R value. The program gives you R squared, what's actually calculated for you, always with the line of best fit, is this R squared value, 0.788. If you square root it, and think about positive or negative, so ours is positive, you can actually like tell if it's weak, moderate, or strong based on the scale. And it's just thirds, so it's a good way to remember. It's 0.33, 0.67. So this is actually a strong positive linear correlation. So we say strong positive relationship. Using the model, we can actually predict values. So there are two types. Interpolation is when you plug points in that are within the range of the graph. So if you plugged in any weekly aboriginal income between 675 and 825, roughly around there, it'll give you a value on the line of best fit. Extrapolation is when you actually plug in a number before or above the domain. And so something above, we'll say like 850, and something below maybe 650. That's extrapolation. Extrapolation is very risky prediction. So you really have to say always if the model was to continue in the same way. To make the predictions, we just actually sub in points to x and y and use algebra to solve for x, or just use arithmetic to solve for y. Individual data points, we can actually make what we call a residual plot in a spreadsheet. So you can watch the other video of how to make the residual plot. And what it does is it tells you how far all the points are from the line. It doesn't really matter what you use for your x value, and I actually probably didn't use the right thing here. It's just a way to indicate where the points are. And so for a point around 975, it's right here. It's actually close to the line of best fit. So you can see that point there is very close to the line of best fit. And so my recommendation would actually be to use year here. So you've got the years up to 2000 and or from 2007 to 2016. So I would actually use the year for x when you make your residual plot. It doesn't really matter what you use for x, but as long as you know what that is, so you can locate where these points are. And so we'll actually see that this point is the furthest from the line. And so if we take that point out, that point actually corresponds to the year 2016, if you look at the data. And so it is the most recent point, but if you take it out, you can actually see the line of best fit. It's really interesting. Residual plot, when you go to higher level stats, is very useful because what you can actually do with the residual plot is if you see a pattern in this shape here, this really should be random. If it's linearly increasing, or there's a quadratic pattern, or there's a sinusoidal, so it goes up and down, what that's telling you is there's some more complexity you need to add to the model. All the ones we do in this course are just linear models. If we remove 2016, 2016 is the furthest away from the line. If you remove 2016, you can see the correlation changing. And it's also interesting because you can say what's happening before 2016. So we've actually increased the correlation and the y-intercept, but you've lowered the slope, which kind of makes sense if you just kind of turn the line a little bit. The y-intercept kind of changes. So as this line turns, if the slope changes, the y-intercept would shoot up a little bit to still go through the trend of the data. Comparing Aboriginal versus year and non-Aboriginal versus year, you can make some conclusions when you look at them side by side. You can see 2016 there that's the way why it's far away from the line. It's a drop in the weekly Aboriginal income. And so you can actually see the slope. So $18 a week is higher. So for every increasing year, the weekly Aboriginal income goes up by $18. The y-intercept doesn't really tell you anything in this case. It's when you have the year 0. So it's just the 18 and the 14 that tell you something. And the weekly non is actually closer to the line of best fit, less consistent for the weekly Aboriginal, although it's still a strong correlation. So I invite you to do is to take the data and try to recreate some of those scatter plots, including the residual plot for Aboriginal income versus year. And there's some practice questions.